Yeah, here we are. So the system looks like that. X1 dot equals, it's a polynomial one, minus x1 plus 4x2. I hope to see this right on the paper. Yeah, I'm seeing it now better. X dot 2 equals minus x1 minus x2 to third power. And the proposed Lyapunov function candidate is v of x equals x1 squared plus we have a parameter here, ax2 squared. Yep. One simple advice, please. If you have a system and you have to try something, if it's a polynomial one, go easy for the quadratic form of Lyapunov functions. And out of this is actually 1 over 2 x transpose px. But you noticed, yeah, if we remain in the notation from last time, so a1 is actually 2. A3 is 0 because we have no cross terms, indefinite sign. And A2 is 2a. Yeah, this is it. If we look at this as it's a quadratic form. Yeah. But to compute the derivative, again, very easy. Dot Vx, we take the partial derivative with respect to x1 and multiply with the derivative of x1. Then we take the partial derivative with respect to x2 and multiply with the derivative of x2. And then we replace the expression of the derivative in the entire computation. So what do we have here? It's 2x1 multiplied by minus x1 plus 4x2. And then the other one is 2ax2. The derivative, I think I don't have to explain this anymore, multiplied by minus x1 minus x2 cube. We'll calculate minus 2x1 squared plus 8x1 x2 minus 2ax1 x2 minus 2a x2 to the fourth power. Perfect. Okay, so there are several conditions we have to check. Is V continuously differentiable? Obviously, yes, it's quadratic form. Is V of 0, 0? Yes, definitely that's the case. Is V of x positive for x non-zero? What does this condition imply? What do you think? I mean, to have a correct Lyapunov function candidate. What does this imply if I look at this expression now? In order to have x1 squared plus ax2 squared positive for every x1, x2 different from 0, what is the condition on A? Of course, A is our leverage here. A is our degree of freedom in this case. So what is the condition on A? Yeah, A has to be positive, of course. Yeah, that's all. Nothing else. Yeah. A has to be positive. Yeah, it's the condition from last time. Yeah, 2 greater than 0, A1 greater than 0, A2 greater than 0, A1, A2 minus A3 squared, but A3 is 0. So this is the condition we end up just to have the right Lyapunov function candidate. Now look at what we have obtained for the derivative. We want this to be strictly negative. Yeah. And now I have red terms and blue terms. The red terms with definite signs are those ones. Yeah, it's obvious that if A is positive, this will be negative, and this will be negative again. But these are definite sign terms. x1 squared is always positive. x2 fourth is always positive. If I put minus 2 and minus 2a with a positive, this will be negative terms. And we remained with the blue terms. indefinite sign. What apply for me now, what we have learned last time. We have to get rid of this, and our leverage is A. So what do we have to do to get rid of these ones? How much should A be? In order to get rid of these ones.
A should be 4.
A should be 4. Perfect. We take A4 and we are done. The derivative is negative definite. We have taken A4. V is a consistent Lyapunov function candidate. And clearly, this inequality is now fulfilled. So for A equals 4, we apply Lyapunov stability theorem, and we are done. Okay, thank you. I think these were 2 examples on quadratic Lyapunov functions candidate. It's one of the classes of Lyapunov functions. Yeah, the quadratic ones. It's just one of the classes. Now let's go back to our last part of the course. Yeah, you remember we ended up with global stability and region of attraction and LaSalle Lyapunov functions. Now, the very first application here, you have also an application with absolute stability, as Tudor mentioned, but the very first application is to make the connection with our linear systems theory. Yeah, if we had the linear system x dot equals ax, we said that the system is stable if all eigenvalues of A were in the left half of the complex plane. But the condition to that, the condition of stability we have imposed for this type of state space system was that x of t goes to 0 whenever t goes to infinity. And the deduction of regarding the spectrum of A went actually or was consistent with the fact that the exponential of the matrix, exponential AT, has to go to 0 when t goes to infinity. That was actually the point. That was actually the point. This meant for us a stable system. And remember, we called it internally stable. It was not the stability regarding bounded input, bounded output. Yeah, as a perspective of input-output way of looking at the system through its transfer function. No, we said that x of t goes to 0 when t goes to 0. Yes, but this was nothing else than writing that the origin is an attractor. Just that for the linear systems, here we have the expression. This is exponential AT multiplied by x0. And in order to fulfill this condition, A had to satisfy the eigenvalue condition, to have all eigenvalues with negative real parts, right? If we look now at the systems from the nonlinear systems theory, so we look from upwards. Yeah, we look with stronger means. We have the Lyapunov function in our hand. Then we get the following result, once again, based on Lyapunov function theory, right? The origin is an asymptotically stable equilibrium point. The matrix is stable, which was stability in this sense, yeah. X of t goes to 0, yeah, when t goes to infinity. Yeah, this was something that we did at linear systems. But then comes the nice result here. Both stability of A and asymptotically stability of the origin are equivalent with the existence of a positive symmetric matrix P, which verifies this inequality. Inequality 9 is called a linear matrix inequality. Yeah? A is given, P is to be found. A is given, P is to be found. And this type of inequality played a huge role in control system theory. Not in linear systems theory, but also in nonlinear systems theory. And the problem was that, yeah, no one knew how to solve that. How to solve something like that? Well, I would say a little bit unfortunate for the development of control theory, but very fortunate of extending the applications which we have been able to tackle. Like 30 years ago, 25, 30 years ago, Russian researchers developed a method, a numerical method, to solve this type of inequality. I have to be sure that I'm quite correct understood here. This sign means that the matrix A transpose P plus PA is negative definite. Yeah, this was explained. I asked you before. This was explained by Tudor. There is a slide on that matter. This one, okay, this one. Yeah, I mean, if we have a quadratic form, yeah, like this one, we call the matrix or like that one that I have written. I have written you that in one of the slides here. I'm recalling that again. It's important. Yeah. If I have a quadratic form of the form x transpose px, yeah, p is called positive definite, and all other definitions apply. Non-negative definite, negative definite, non-positive definite. If and only if, yeah, this is definition, x transpose px greater 0 for every x different from 0. Yeah, so for every x, this is very important. And p is called, I repeat, positive definite. All other definitions can boil down from here. Yeah. So when I write A transpose P plus PA lower 0, this is in this sense. This is that this matrix is negative definite. So for every x non-zero, if I put x on one side and on the other one, I obtain here something which is negative in value. This is a real number. This is also a real number. So do not forget about the significance of these things. Keep it in mind. So this was a huge breakthrough, honestly, huge breakthrough. What did people before having this breakthrough in these numerical issues? Well, they solved instead the Lyapunov equation. You see, if I take this, Tudor, here is the typo. We have to have a minus here.
This is, I will correct this using my pen on the tablet.
Yeah, okay. Do it. Not now, but you can do it. Yeah,
but I think they understand it's a mistake there.
Yeah, no, it's obvious from equation 10. Yeah, but the point is that instead of solving the inequality, one can take any positive q, you solve the equality, and the solution, also numerical one for the equality, was known, and then you of course get the inequality because A transpose P plus PA will be minus q. Here is a minus. Okay, and it will be obvious negative definite. Yeah, or the solution P of the equation has an explicit expression. Of course, you will not calculate it like that. You will calculate it through numerical methods.
It's a Gramian, actually.
Yeah, Tudor, not only that. It would be a Gramian if I would write here.
In particular, if Q is the particular case C transpose C,
Tudor, we will have the next slide on that.
Oh, okay.
We'll have the next slide on that. Okay, so yeah, this is an equation people know to solve, and I tell you very simple why. Because this is a linear equation in P. Obviously, it's a linear equation in P. Let me show you one. Yeah. Assume, for instance, A. We know this is a stable matrix. Yeah. It's diagonal eigenvalues on the diagonal. Yeah. And now I will take Q identity 2 of dimension 2, and I write the equation A transpose P plus Pi plus Q equals 0. Q is obviously positive, yeah? And I want to find a positive P on that. Well, we have a solution here. We will have three unknowns, yeah? I have P1, 3, P3, P2, yeah? Plus P1, P3, P3, P2, P is symmetric, of course. Yeah, P is the symmetric matrix, multiplied by minus 1, 0, 0, minus 2, plus 1, 0, 0, 1, and all this is 0. And now I take every component of that, and you have a system in unknowns, P1, P2, P3. There is a sound numerical way to compute that, but guys, this is a linear system. Yeah, it's a linear system. It's important. It's not difficult to solve. You can do it even by hand. Look what I have written here. I will not go into the details because we want to finish some things today. But just to understand, this is a linear system of equations, nothing more. So don't be frightened about that. Yeah, all these things, let's say, are actually contributing to the proof. One is equivalent with 2, we know from linear systems, and here the proof is very simple. We take the quadratic form as a Lyapunov action candidate. We compute the derivative. Yeah, the derivative of x transpose px with respect to the time is computed like the derivative of a product. Yeah, it's a product. So first I have derived the first term, and then I derive the second term. But x dot is x transpose A transpose. X dot transpose is x transpose A transpose. And x dot is AX. But we have x on one side, x on the other one, and we end up with this. Yeah. So if you want this negative, this has to be a negative definite matrix, and that's it. And now for the other one, you look at 2 implies 3. Because A is stable, you take any Q, you write P, and because A is stable, this improper integral converges. So this is a positive definite matrix. And if you introduce it into that equation, you will see that the equation is verified. And that's it. Yeah, it's a simple proof. Tudor, you said we will not go into details, but these are two important things here. Yeah, this is called the Lyapunov.
This is a constructive proof. I was talking about the other proof.
Lyapunov equation because you construct a Lyapunov function candidate.
Exactly.
So it's exactly the theory before which goes and brings you to the formula 10, or eventually to the formula 9 is what you prefer. Today we have numerical methods both for this as for this, so you can choose whatever is simple. Yeah. So it's precisely the point I have addressed. How to check that it's positive definite? You determine a P satisfying this LMI, which can be solved efficiently from numerical point of view, right? But you can also take the Lyapunov equation solution. Yeah. In both, I mean, the LMI directly brings you, if it's solvable, if it's feasible, that's the expression. If it's feasible, it brings you a P which is positive. Well, if you solve the Lyapunov equation, you still have to check that P is positive definite. If we will have 5 minutes at the end, I will show a little bit things on that matter. And now we are going towards the direction you want.
Yeah, this is a nonlinear problem. It can also be solved with the Hamilton-Jacobi equation for the nonlinear case, so it has been proven. It's a good example.
Yeah, Tudor, I think if you could add an example with a bilinear system, no, in this case.
Yeah, probably. Yeah. I'm not a big fan of bilinear systems.
Yeah,
this is something that comes from Astolfi. He hates them. Yeah.
Okay.
He says bilinear is not linear, is not non-linear, it's just fake stuff. I'm kidding.
Yeah. Now, if we take the same Lyapunov equation, but we take instead of Q, we take a product of the form C transpose C, where C is a matrix of appropriate dimension. But C is not a square matrix here. Yeah. C is a matrix of dimensions Pn. Yeah. Of course, this one is an n. It's like the C matrix from the linear system. Okay.
That's exactly what it is.
Yeah, could be as well, Tudor. But for your taste, is exactly what it is.
Yeah, because we are talking dynamical systems.
Yeah. Okay. So if the pair is observable, and we have a positive definite solution to this equation, then you have an asymptotically stable equilibrium. This is a very nice application of the Lyapunov functions, which are of LaSalle type candidates, right?
Exactly.
So we take this Lyapunov function candidate. Yeah? It's easy to see its derivative if we take the quadratic form for linear systems. Yeah, you have to keep in mind we are at a situation x dot equals ax. This is the linear system, and now you take the derivative. Yeah, the derivative brings as a quadratic form A transpose x plus xa. It always does this. Whenever you take a quadratic form as a Lyapunov function candidate for a linear system, if you take the derivative, you will end up with this term. So we ended up with this term. Yeah, we took x instead of p here. Yeah, but if we look at this equation, we see that we actually get minus x transpose c cx. Yeah, but this is nothing else than a vector, the vector cx, multiplied by its transpose. Yeah, but this is the norm squared. Yeah, it's sum of y. It's sum of the component of the squared components of the vector. So it's minus the norm of the vector squared. And this is always lower equal 0. Yes, but it's not strict lower than 0. So we cannot assert the negativity of W, but the non-positivity. So how to achieve now that the origin is an asymptotically stable equilibrium? Well, let's have a look where W gets equal to 0 and check if this set contains other solutions than or except the trivial orbits. So we check the set calligraphic N where W is 0, and we have to ensure that we have only the trivial orbit, not other trajectories. And we do that. Tudor, vorbește cineva și n-aud? Is something telling me something and I cannot hear it?
I can't hear it. I'm only hearing you.
Yeah, but I had the impression that someone wanted to talk, but okay. There is no question.
I'll ask a question later about this proof.
Yes. So Cx, where is W 0? When the vector here inside of the norm is 0, which means Cx is 0, meaning x in the kernel of C. Okay. But any trajectories which is in kernel of C is automatically in the non-observable subspace of the pair, because the non-observable subspace is constructed like that. Yes, Cx is 0, Cax is 0, Ca square x is 0, and so on and so forth. Yeah. So once you are in the kernel of C, then you have all this equality equals to 0. Yeah, but we assume that the pair is observable, and for observable pairs, the non-observable subspace reduces just to the origin. We have just one point which belongs to this space, right? So in this under these circumstances, yeah, under these circumstances, because of the observability, we have just a trivial solution. And the Lyapunov stability theorem in the LaSalle form applies. So we can deduce that the origin is an asymptotically stable equilibrium point. Yeah. Okay. There is a very important thing about these results on linear systems. And this very, very important thing concerns the fact that we can decide on the stability of the origin for a given nonlinear system without being obliged to find or to invent or to retrieve a Lyapunov function. Yeah. We just rely in deciding about the stability of the origin on looking at the Jacobian matrix associated to the vector field F. Yeah. So A is just simple, yeah, the Jacobian matrix of the vector field F calculated at the origin. Yeah. You will understand a little bit later why these things comes into play and what the role of it and what is the role of it. Now, look first at the theorem. The first point, if this Jacobian matrix is stable, meaning it has all eigenvalues in the left half, complex plane, yeah, meaning all have negative real parts, then the origin is an asymptotically stable equilibrium point. Yeah, you see how strong this result is. I have an arbitrary non-linear system. I'm looking at the Jacobian matrix and I decide whether the origin is stable or not. I don't have to look for a Lyapunov function because Lyapunov looked for us. And the candidate which is employed to prove that is, of course, the quadratic form which we use for linear systems. Okay. Point 2. If at least one eigenvalues of A is non-stable, yeah, it has positive real part, yeah, then the origin is an unstable equilibrium point. Once again, we're not talking about eigenvalues on the imaginary axis. No. I have to find at least one which is in the right, not on the in the right, not on in the left half plane. Just one. If I have found just one, it's done. The equilibrium point 0 is an unstable equilibrium point for the system. Okay. What happens if A is, as we called it at the linear systems theory, marginally stable, or let's say stable in not strict sense? What happens if you have eigenvalues with 0 real part, which are on the g omega axis? Well, this is from my perspective, the most interesting situation. You cannot conclude anything about the stability of the equilibrium of the origin. You don't know. Decide just on the information regarding the eigenvalues of A. You can decide if all eigenvalues have negative real part. You can decide if at least one has positive real part. But if you have eigenvalues with negative real parts and some of them are on the g omega axis, you cannot say anything. There are examples which give you both many situations. I mean, could be stable, could be unstable. Anything can happen. So you cannot decide. Yeah. So why was the theory before important? Why was this so important? Yeah. This Lyapunov function candidate. Take a look. We'll not go into the details of proof, but take a look. The idea is to express f of x by a mean value theorem. So you mainly develop in series, but here instead of writing the first order term in the Taylor series where A comes into play, you take a mean value theorem and you write an exact expression for f. But yeah, zeta is a point on the segment 0x. And what did we do? F of 0 is 0. Yeah, so this term does not count. But then we did a trick. We added the Jacobian evaluated in 0, which is A, and then we equally subtracted it. Yeah, because otherwise we don't get the right expression here. So the expression of f is this one. And we added ax to this, and we subtracted it from this. Yeah. So we end up with this expression, ax plus g of x, and g is this one. Okay. And now the claim is the following. We'll prove that the origin is asymptotically stable by taking the Lyapunov quadratic form associated to A, to the Jacobian matrix associated to the vector field F. So A is stable. If you take the Lyapunov function equation. Yeah, you take A is stable. Yeah, you know that A is stable, and then you find a unique positive solution P. And then you take this Lyapunov function candidate, which is, of course, the right one for x dot equals ax, but you take it for f, for the vector field. You write the derivatives, yeah, x transpose p x dot, which is f of x, f transpose of xp, yeah, which was x dot transpose, and you end up with this expression. So the linear part will show with the term we know from the stability of linear system, and of course this g of x term gives you an expression of this type, x transpose p g of x, and it's 2 times the same quantity. Yeah, this is here also the 2 times the same quantity. What do we know now? So A transpose PA is minus Q. So here we end up with minus X transpose QX. And here we remain with this term. And now the fundamental role is played by the fact that you can write these things in a very, very small neighborhood of the origin, as small as you want. And here is the technical trick regarding that. You see, when x goes to 0, g of x goes to g of 0, which is 0. So g has a certain continuity property around the origin, meaning that, yeah, if you have a given gamma, you always find the delta gamma, such that the norm of g of x is bounded by gamma norm of x. It's because of the definition and the certain continuity property with x. So if x is small enough, g of x in norm is bounded by a given constant x in norm. And this inequality, which again, it functions locally, it's in a very small neighborhood of the origin, as small as necessary to achieve this inequality. Yeah. Then this term, which is a real number, you have here a usual inequality between modules and norms, can be actually bounded by the norm of P. It's the induced second norm, and the square norm of x. And now the derivative is minus x transpose qx plus 2 gamma norm of P, norm of x squared. Yeah. Moreover, the norm of P, because P is symmetric, will be lambda max P. And the only thing that we have now, what is our leverage here? It's gamma. I told you, we can go with gamma as low as necessary. We just want this inequality to hold, but it holds because of continuity of G. And then if I pick gamma small enough, it doesn't matter how great the minimum eigenvalue of Q is and how small the minimum eigenvalue of Q is and how large the maximum eigenvalue of P is. No, it doesn't matter. Gamma will be chosen like that, as small it comes out, and for this gamma, we guarantee the W is negative. And we are done. We are absolutely done. Yeah, it's a little bit of linear algebra here, but once again, please don't go into these technical details. There are some developments where they are useful, but just remember the idea. Yeah, if the Jacobian matrix is stable, it has all eigenvalues with real negative parts. I just take the Lyapunov function for the linear part of the system. Yeah, let's say that x is the linear part of the system, and this Lyapunov function is a good candidate for the nonlinear function. Yeah, that's all that that we have here. Yeah, how late is it? Yeah, I think Tudor, we should stop here. Maybe I will take just 5 minutes to illustrate point 1 with our last example. This would be the only thing I still would like to.
I have a short comment. I think that this result is very strong. However, it's more restrictive than the Lyapunov theory in general, because in most cases you may run into the third situation.
Yeah, Tudor, absolutely.
So what do? You have to still build the Lyapunov function. So
yeah, absolutely. You don't get rid. This is also very good comment. This is also what is called stability in the first approximation. In the sense that you approximate your nonlinear function with its linear part.
We saw that in the second order system.
Yeah, and you are right. You know, most example where this thing holds immediately is with simple examples.
Exactly, because and usually also number 3 falls on the center case we studied in the second order systems case, when you have the pendulum without friction, for instance.
Yeah. Yeah.
Situation number 3, and that's undecidable because the center, you don't know whether it's stable or not.
Absolutely. You know, it's not. There is another weakness of this result, if I can call it like that. Yeah, imagine you have a bigger system, an nth or 10th or 8th order system.
Exactly.
And you end up with a matrix in some parameters. Yeah, you don't know if it's stable or not.
Of course, and the parameters are probably uncertain as well.
It's easier to find maybe sometimes it's easier to find an appropriate Lyapunov function.
Exactly.
Than to decide that the eigenvalues of the linearized or the Jacobian are sure. No, it's
a tough problem, and again I go back to the main theoretical philosophy. All of this is necessary, is sufficient conditions, not necessary, unfortunately. That's the issue. That's the big issue here.
Yeah, that's the big issue. But anyway, we don't know, Tudor, we don't know better. You see
Yeah, because we don't have global results. That's why this is all local.
Yeah, we don't know better. This is the best what we can do.
And we cannot
And
do.
in practice,
better.
In practice, we work around this this equilibrium points. Okay. Now this is now the last example I have picked up. I write it again on the board. Yeah. So what is this A? What is this f prime of 0? Yeah. So we have here x dot equals fx. Yeah. Or as we write it, df dx. I write it in a point x in general. Sorry, I will write it in general in point x, just to have an idea. So this works like that: df1 dx1, df2 dx2. Sorry, df1 dx2, df2 dx1. It's easy. df2 dx2, and of course everything in a given point x, right? Okay, equals to, in this case, come on, this I was close to say a bad word. Yeah, and now we have to look at the equations. So equals what? F1 minus 1. This is linear. df1 to x2 is 4. df2 to dx1 is minus 1. df2 to dx2 is minus 3x squared. I hope I'm not wrong. Yeah. No, and now if you take x1 0, x2 0, this means in 0. Yeah. F prime of 0 would be minus 1, 4, minus 1, 0. Yeah, you have now to compute the eigenvalues of this thing, which is what? Is lambda plus 1, minus 4, 1, lambda. Yeah, it's determinant of lambda I minus f prime of 0, minus a, sorry, minus a. Yeah, and what is that now? It's lambda squared plus lambda.
Plus lambda minus determinant, 4, plus 4.
Plus 4, yeah. And this is a second order polynomial with all coefficients having the same sign. It's a Hurwitz polynomial.
Exactly.
So yes, A is stable. It's obvious from here. Yeah, A is stable, and according to the first approximation theorem, 0 is asymptotically stable equilibrium point. Yeah,
exactly.
Yeah. So this is the point. Yeah, origin is an asymptotically stable equilibrium point for that system. Yeah. Of course, it's an equilibrium point. If I put here x1, x2, both 0, but this works like that. And I have for you a nice exercise, and we close now. Please calculate all equilibrium points of the pendulum equations. Calculate everything there. Where were we with those things? Here. Yeah. So please, equal to 0, these two expressions, x to 0. Yeah, we have them. I have written them. Yeah, x1 is kp, and x2 is 0. Right? We have computed them here. And now, please use the stability theorem in first approximation to decide which of these equilibrium points are stable and which of them are unstable. I tell you that you will not end up in the third situation. You will end up in the first and in the second situation. And you will retrieve your intuition about the physical system. So this is the exercise.
That's all depending on the friction, depending on the K or B or what is there, the friction coefficient.
So Tudor, it's important to have the friction. So
Without
K
friction,
non-zero,
it's gone.
K non-zero, that's very important. K non-zero.
Exactly.
Yeah. But as you imagine, these Jacobian matrices will depend as well on this K, you know. I should have written here n pi, not k pi.
They understand.
Yeah, I know they understand, but I will write n when I will correct that. And
I will make this an assignment because they need to corroborate this with the previous chapter, with the center and the focus and the nodes and all that.
Yeah. Of course. This is this was an important issue there, Tudor. Of course.
Yes.
But this is the exercise. Please do it. It's important to do it and to see how with good theory you retrieve immediately the intuition of the physical
Physics.
Yeah. So when n will be even, you will have stability. It's the downwards. And when n will be odd, you will have non-stability. You will have one eigenvalue with positive real part. Yeah. While when n is 0, 2, 4, etc., you will have eigenvalues which are stable. Yeah. Okay. Yeah, Tudor, I think that would be all. I was enough. 10 minutes more later than I intended, but
that's nice. It's the first time when we have all the 3 hours.
Tudor, they would not like me they would not like me.
Yeah, but in the rectorate, if they check us, they'll give you a prize because you're the only one doing all the hours by the book.
I don't think idiot enough to start to look for this.
No, I'm having a different philosophy. Master classes is wrong to have.
Honestly, on the other hand, it's also very wrong to get money for some courses.
I agree, but this is the system itself is
sure. We don't need the recording anymore.